Hey, my at-home warriors. This video here is about breaking down. What are we breaking down? We're going to talk about classes of matter and phases of matter and the difference. So you should have just finished up content on branches of chem and the scientific method. Hopefully you made it through a couple of the questions in the section review for that. And the next up would be what you see here. So let me share my screen with you. Okay. All right. So if we're going to talk about classes of matter, phases of matter, and like properties that they have, got to have kind of a definitional slide in here because there's a lot of terms that'll start showing up that I just want to make sure if you ever get confused, you can pivot back to this to see what it is we're talking about. All right. So if we work our way down, there are characteristics of stuff called matter. And you're going to say, well, what is matter? And matter is pretty much everything. Matter, by definition, is anything that has mass and takes up space, which, other than the thing called antimatter, is everything, because everything is made up of atoms and particles and things of that nature, which all will take up space, even if it's infinitesimally small and you can't see it. It is matter. So because the matter takes up space, it creates two things: mass and weight. And you're going to say, well, I always thought those were the same thing. Like, weight's how heavy it is, isn't that the mass? Well, mass is measuring how many pieces of matter there are. Think of it like counting up all the M&Ms that are in a bag. All right. If I take that bag of M&Ms and I put it on the moon, there are still the same number of pieces. All right. Of M&Ms. So its mass never changes no matter where we are. Our balances in the lab measure the mass of substances. Weight, on the other hand, factors in gravity. And because gravity isn't constant, you will see varying weights. For instance, if I were to get on a scale, which is how you measure weight, it's going to say I weigh about 180 pounds. But if I take that scale to the moon, the gravity on the moon is only 1/6 what it is on Earth. So if I were up on the moon and I stepped on my scale, I would only weigh 1/6 of 180 pounds, which I don't know why I took out a calculator. I would weigh 30 pounds. Sorry, I had the right, nice round number. Right, so weight and mass are two different things. Mass is measuring the number of pieces of matter, and the weight is measuring that matter with gravity also pushing on. So I threw out some terms, even just explaining that. Things like atoms and things like particles and things of that nature. Right, so an atom is the smallest piece of an element. So there's some terms that change based on how complicated the matter is. So on the bottom of this slide, I always have 3 bullet points that help to hopefully make you stay organized as you go through. Bullet point number 1, and you want to write this down if you have your PowerPoint printed out, is this. You have atoms of elements. All right, so on the bottom of this slide, you would write, you have atoms of elements. Second bullet point, you have molecules of compounds. So the second bullet point says you have molecules of compounds. And then the third bullet point explains the difference between those two things. All right. Molecules are made up of atoms that have lost their properties. Molecules are made up of atoms that have lost their properties. All right, so to show you the difference of what I'm talking about, it's a great time to use some models that I can show you. All right, if I were to show you a picture of an atom, it would look like this. Imagine it to be like a tiny sphere. And if I were to get more of them, it's just more of that sphere that aren't connected. Right? Now, what that sphere looks like will control what it is. For instance, if I showed you my ring here, this ring is white gold. It's 24 karat white gold. That's pure gold. It means you are looking at billions of these guys just stacked on top of each other. But they're all identical, all atoms of gold. Now, when we start looking at some other things and we start connecting these atoms, I'm going to imagine these were hydrogen atoms now. Now, hydrogens have their own unique characteristic. Hydrogen atoms are gases by nature. They're flammable by nature. And if I took a different atom, like this red guy, that's an oxygen atom. Oxygen have their own characteristics. Right? Oxygens are also gases. Right? Oxygens are breathable into our body, so are hydrogens. Right? But if I all of a sudden start connecting these things, right? They're not just separate from each other. I connect two hydrogens that are gases that can catch on fire to an oxygen, which is a gas that we can breathe. All of a sudden, I get H2O. And because they're connected, this is a molecule. And when you form these connections, all of their properties changed. Water, H2O, is not a gas. Water, H2O, is not flammable. Water, H2O, is not breathable. All right, I can't get it in my lungs. It'll suffocate me. Like, there's your difference between atoms and molecules. Molecules are these guys, and that's what compounds are made of. Atoms are these guys, individual spheres, and that's what elements are made of. So you have atoms of elements, you have molecules of compounds, and molecules are made up of individual atoms that have lost their properties. All right, so that's one of those things that it takes a little bit of time to digest. The other stuff that you're seeing on this slide are all just definitions that you will see us use later on throughout the PowerPoint. I just dump them all onto the same page in case you need to go brush up on a definition. We will talk about energy, particularly when we're talking about heat and movement of molecules and why certain phases look certain ways. Like, there are two types of energy. You've got kinetic and you've got potential. Kinetic energy is energy of motion. If an object is in motion, it is using kinetic energy. It has kinetic energy. Potential energy is stored energy. This energy can take a lot of different forms, but think of a stick of dynamite. Inside of that dynamite, you know there's a lot of energy because once I ignite it, a massive explosion gets released. That's potential energy. It's stored. It usually comes from the energy that's in these bonds that hold things together. And when we break those bonds, all right, and we form new ones, energy can get released. And a lot of times the new bonds formed release a lot more energy than the ones that were broken. That's why we get explosions. But we have these laws that controls these things. And each of them sounds sort of similar. They all say cannot be created or destroyed in a reaction. Right, so we must conserve energy. If I lose potential energy, I must gain other energy, maybe kinetic. When my bomb goes off, I lost potential energy. I better gain other energy. I do. It's really hot. I gain thermal energy. It exerts a lot of force on me. I gain kinetic energy. Mass is the same thing. I must conserve mass. I can't create it. I can't destroy it. And it's because of the next law. I have to conserve matter. Right? So I am allowed to take a molecule and rearrange it. I can pull pieces off and connect them in different fashions. But what I can't do is destroy any of these white spheres or this black sphere, and I can't clone them. I can't replicate them. I'm allowed to rearrange them, right? I'm allowed to break them apart and have them be separate, but I can't create more of them and I can't clone them. And because I have the same number of pieces before and after, their mass has to hold constant. So for instance, if I had you walk into the back of the lab and weigh this piece of paper, you would get a certain mass of that. If I were to then light that paper on fire, right, and I were to take the ashes that were there and I were to trap the gas that was getting off, the smoke and the fumes, and shove it all back on a balance, those two numbers would be the same because matter and mass must be conserved. So these are ideas that kind of control some things that we'll see as we go throughout the year. All right, so if we're talking about matter, and we've already had the idea that there's a couple different types, I wanted to talk about our classes of matter, which I've touched on a lot of these terms. All right, so like I said, we've got this big category of stuff that's everything called matter. All right, so how do we know what to subdivide it as? Well, we ask ourselves a question. Can I physically separate it? So if I can take this thing I'm looking at and physically separate it into pieces, it is known as a mixture. It's a mixture of two or more different types of matter, but they keep their properties. All right, now, if I look at that and it looks like one thing, that means it's a homogeneous mixture. Oh, sorry, I went the other way. All right. If I can't separate it physically, right? If I try to filter it and I can't, if I try to get it to react and I can't, for instance. Oh, no, there we go. Sorry about that. All right. If resetting, if I can separate it physically, it's a mixture. It's a blend of two or more types of matter, but they keep their properties. A homogeneous mixture looks like one thing. Right? For example, my coffee in the morning is a mixture. All right. In class, I would ask you guys to list the components that are in that. And those of you who are coffee drinkers, you'd say, oh, okay, I know there's water in there. Right? Other people would say, well, hey, isn't there like coffee in there, coffee grinds that are dissolved up? Absolutely, yes. Someone's going to say, oh, yeah, I have to have coffee. I got to get my caffeine. That's in there. Like, I don't like my coffee black, so I put cream and sugar in. But even though I've got cream and sugar and coffee and caffeine and water all in there, when I mix it all up, it looks like one thing, right? If I dump it out on the counter, it looks like creamed coffee. But that's called being homogeneous. But I know all of those different things are in there because I'm still able to drink it because it's mostly water. It doesn't hurt me. It creates energy for me. I know that caffeine's in there. It's sweet. I know that sugar's in there, even though it looks like one thing, right? The creamer's in there, right? It's not like that black coffee taste, so I know the cream's in there. So if it looks like one thing, but all the pieces are still in there, it's known as being homogeneous. I listed some others on the bottom. Like the air you breathe isn't one thing. You take a breath, you breathe it out. You just took 5 or 6 different things down into your lungs. The thing you need the most of is your oxygen. It's what your body works on. What's air's main component? It's nitrogen. About 70% of the air is nitrogen. You're breathing in some carbon dioxide that's floating around. You're breathing in some hydrogen that's floating around. You're breathing in some helium that's floating around. All of these went down into my lungs, and they stayed the way they were. The oxygen was still oxygen, so my body could use it. The nitrogen, I didn't use, so I breathed most of it back out. The carbon dioxide that was in my lungs that got dropped off by my hemoglobin, that gets breathed back out, and they keep their characteristics. All right, now, if I have a mixture, it's 2 or more different things, and I can see the difference between those things, it's heterogeneous. For instance, All right. If I eat a salad, each one of those things we know is different, but I can mix them all up. And the one thing is called a salad. It's a mixture, but they all keep their properties. The lettuce tastes like lettuce. The tomatoes taste like tomatoes. The cheese, the chicken, the steak, the French fries, if you're getting a good salad, they are all having their same characteristics that they always do. But the difference is I can go in and pick the tomatoes out individually. I don't have it be one blended salad where I can't see the different pieces. There are some others you might relate to. If you have granite countertops at your house, you've got these black countertops with these little speckles in them, right? That's a mixture. We call it granite, but it's got different components, but we see the difference. All right. Now, if we look at our thing and we can't separate it, right, physically, I try to filter it and it doesn't work. Right? It is one of two things. It's a pure substance. It is either an element or it is a compound. Right? So if it's an element, we already talked about this. It's one type of atom just repeated over and over again. It cannot get more simplified. Right? Gold, silver, oxygen, anything that's from the periodic table, which is sitting up there. Anything from the periodic table is an element. It's a pure substance. Gold, silver, all the things that you guys know. Compounds are also pure. All right, and this is where it gets kind of tricky. Compounds are pure as well. They're made of multiple atoms stuck together with bonds, but it's that thing repeated over and over and over again. So if I were to bring in another one of these molecules and you were looking at them side by side, that's a compound. Yeah, there's multiple pieces, but this piece that I just put over there to the right is identical to this piece, which I just brought in from the left. Right? So compounds are things that are a mixture of two elements. So lots of times if you're seeing more than one element from the periodic table named, carbon tetrachloride, octasulfur hexasulfide, all right, things like that, those are compounds. The ones that actually trip you guys up the most are the ones we give everyday names to. Like water, is H2O, but because it says one word, it makes it feel like it's an element, but it's not. It's hydrogen and oxygen off the periodic table put together. That's two elements, makes it a compound. All right. Sugar, right? Sugar sounds like one thing, but Mrs. Sherry taught you sugar is C6H12O6. Well, glucose is. That's a sugar, right? It's got carbon, hydrogen, and oxygen all stuck together. That can't be an element. It's got multiple pieces to it. All right. So usually what we do to finish up the day, is we go to the back and I have you look at a real world substance, what it looks like. And then I have you look at what it looks like on the molecular level, all right? And when you do that, hopefully it gives you a better idea of which class of matter that you are in. All right, so hang tight for like 15 seconds while I go get the stuff I need from the back, all right? And I'll walk you through it up here. Be right back. Almost back. Okay. All right. So what I have you guys do is go to 4 different stations. All right. Because we've got homogeneous mixtures, heterogeneous mixtures, elements, and compounds. And then what I do is I show you a real world sample of something like this. And then I show you the molecular substance, what it looks like at the atomic level. So this guy. All right, so the first station you go to is this one. Here's what these guys look like. All right, and you guys can look off your own PowerPoint. And I'll bail out of that, stop sharing my screen so I know you guys are seeing nice and big what I'm holding up. So I'll put them right back there for you. All right, so here's your substance. You might think you know what that is. And here's what it looks like at this tiniest level. So what I want you to do, all right, is on the bottom of that slide where we have our little flow chart of classes of matter, all right, is I want you to say, is the first one homogeneous mixture, heterogeneous mixture, element, or compound? So here is category number 1. All right, move those off to the side. Here is category number 2. So here's your real world sample. That's what you're looking at. Here's your molecular world sample. So you guys are allowed to dump those out. And I can sort those out so that you can see them. All right, now for this one here, you're getting the same thing over and over again, and that's what that piece looks like. So again, take a second, tell me, do you think that that is a homogeneous mixture, heterogeneous mixture, an element, or a compound? All right, so I'll clean those up while you're jotting that down. Okay. Category number 3. Here is my real world sample. Here is my molecular world sample. So my real world sample looks like this. And if I dump out my molecular sample, this is what was inside that beaker. And I had a bunch of these guys. Okay. And then I had one of these guys in there. And so again, what are we looking at? Is it heterogeneous mixture, homogeneous mixture, element, compound? Okay, put that back. And then the last station that you pit stop at is this guy. And to be dramatic in class, I usually say, okay, here, let me fill this, which is ironic because it was already filled. All right. And that's what it looks like in there. But if I show you the inside at the smallest level, right, this is what you're seeing. A couple of these, bunch of those, couple of those. All right, so last but not least, tell me, what do you think this is? Heterogeneous, homogeneous, mixture, element, or compound? All right, and then what we do is we break it down together. All right, so I'll take you back to the first one, which was this guy. All right, and then usually I say, okay, what were we working with here? And people are like, okay, copper. And I'd say, okay, what is that? And then hopefully they'd come back and say it's an element. But then we talk about why it's an element. So I'm looking at this in the real world, but notice if I look at this guy, right, it is just the same thing over and over and over and over and over again. Like this is a sheet of copper that would be held together by what we call a metallic bond. All right, so it's this one black sphere just repeated. That means this is an element. All right, the second category was this guy. In the real world sample, people say, oh, okay, that's water. I know it's water. And I said, okay, let's look at these. All right, and hopefully we come to the conclusion that water is a compound. And the reason being is, look, every piece that is in here is identical. They are all the same, just like the last one. But the big difference is the individual piece has more than one type of atom in it. So because we've got two H's and an O, this guy, all right, is a compound. But notice it's still pure. Every single piece in here is H2O, right? I never see them separate. That is what makes it a compound. The third one I showed you guys was this. All right, and obviously this is a mixture. Now, when I dump out the pieces, here's why I know it's a mixture. Fundamentally, I am seeing two different things here. I am seeing an element and a compound, and because these guys aren't identical, that means it's a mixture. It's a mixture of this compound with this element. Now, you can't decide if something's homo or heterogeneous without seeing the real world sample, right? So when I look at this beaker, it is very easy to see the difference between the copper and the water. So because I can see the difference, I know it's heterogeneous. I see the pieces. And then the last one I showed you was this guy. Looked like an empty beaker, and we know the beaker's really filled with air. I dump the pieces out. I know it's not an element because it's not all orange spheres over and over again. I know it's not a compound because I'm seeing fundamentally three different types of pieces. I'm seeing oranges, I'm seeing greens, and I'm seeing these blue purples. Right? So I know it's not a compound. So that means it's either a homogeneous mixture or a heterogeneous mixture. I can't tell which until I look at my real world sample. And because when you look at this, you're like, I don't know, it doesn't look like anything. It's because you can't see the difference. It all looks uniform. It looks like one thing. It is a homogeneous mixture. So that last one is a homogeneous mixture. All right, so these are our classes of matter. All right. Second thing we look at is we have phases of matter. All right, so I'm going to share my PowerPoint back with you again, talk to you about phases, and get you out of here. Okay. All right. So if we're looking at phases of matter, what controls your phases of matter, right, is simply how far apart your particles are. The closer together your particles, the more likely you are to be a solid. The further apart your particles are, the more likely you are to be a gas. So if my particles are close together, it leads to certain characteristics. It says I've got a definite shape and a definite volume. And it's because it's got strong connections that hold everything together. So when I tip it, nothing happens. In a liquid, it's kind of like in between. The particles touch, but they're not so connected that they're stuck in place. They can slide by each other, which is why you can pour liquids. Right? This means they have a definite volume, but they don't have a definite shape. Right? Whatever's in here right now is the coffee cup shape. But if I dump it into one of those beakers, now it's beaker shape. And your gases, they're so far apart, right, that they don't have a definite shape. And if I take the lid off, this gas spreads out. All right, which means it doesn't even have a definite volume because it's got really, really bad attraction forces. All right, now there is a fourth category. It's called a plasma. All right, we don't work with them much because usually they only exist on super high temperatures where basically it's a gas particle, but it's knocked the electrons off of it. All right, which can happen. But if you want to learn more about that, you got to take me one more year for AP Chem next year. All right, and just to show you what's going on with energy, solids have the least amount of kinetic energy. They're not moving very much, right? All they can do is vibrate just a little bit in place. Liquids can slide by. They have more movement, and gases are moving like maniacs, so they have the most movement. But if I put them all in a container together, all right, the solid, notice, holds its shape. Even though it's sitting in a beaker, it doesn't look like a beaker. That's definite shape. Right? If I have a shape like a cube, I could get its volume, length times width times height. That's its definite volume. If I take that solid, this guy here, and I melt him into a liquid, there's the same number of pieces. They'll take up the same amount of space. All right? That's why they have a definite volume. But the shape changes, right? They aren't stacked the same way as they used to be, so the shape is indefinite. The gas, on the other hand, if I heat this thing up, now they have enough energy they can break apart from each other, which means some of these guys get the space out a lot more. And now they don't just take up the bottom part of the container, they take up all of it. That is indefinite shape and indefinite volume. So usually I'll use properties of matter to kick off the next class because we get into reactions, which are chemical changes. But this gives you a lot to work with if you guys are going to keep chipping away at your section reviews. And remember, those section reviews are due on Friday. I hope you guys are still doing well. Hang in there. I look forward to getting you guys back in class. I'll send one more video your way, which is about reactions and types of elements. That finishes the PowerPoint. And then we'll be in the lab later in the week. And I've got a little mini activity for you guys to work on between here Wednesday and Thursday. I will talk to you guys soon.